conductor wound on a, let me take another color right here. See here. If you wound a conductor on a magnetic material or non-magnetic material, it is known as a solenoid. So what is the example for this one? Suppose if you take a transformer core, yeah, everybody knows about the transformer core. If you take a transformer core, this is a transformer core which is made up of silicon steel. And how the primary winding is wound on this core here? This is the way. These are called limbs. On the limbs we are wounding the coil. The copper wire is wound on a magnetic material, and non-magnetic material is known as a solenoid. This is a solenoid. Okay, this is called a solenoid, and this is what a core material, or like a silicon material, transformer core material. Here we have taken only one limb here. And the length of the solenoid is what? Length of the solenoid is L. Length of the solenoid is L. And the radius means from center to this one. Radius is A. And how many number of turns it has? N number of turns. Let us, N number of turns is going on this coil, on this core. And it is carrying a current I. So it is carrying a current I in this direction. In this direction, the current is flowing in this fashion. Current is flowing in this fashion. This is the problem. This is the data. A solenoid of length L and radius A consists of n number of turns of a wire carrying current I. Now, show that at point P means any field point along its axis. Yeah, can you guess what is the axis of this solenoid? What is the axis of this solenoid? Axis means where the axis is exist for the solenoid. Please respond. Am I audible to everyone?
Yes, sir.
Yeah, how the axis is exist for the solenoid? At the
Horizontal.
Yeah, this is at the center. This is an axis. This is axis. Now where this point P is exist here along its axis. Let us assume this is the point P here. What is the point P here? A field point. Field. What do you mean by field point? It is the point where magnetic field intensity is to be calculated. Okay, along its axis E is equal to H equal to Ni by 2 cos theta 2 minus cos theta 1 into Az. This is the answer. This is the what we call derivation which we are going to derive for this solenoid, where N, what is the small n here? Number of turns per unit length. Suppose, what is the n here? N is the total number of turns. Total number of turns. That is 1, 2, 3, 4, like that. Let us n number of turns are there here. Small n is equal to.
Someone wants to join.
Okay, right. Henu, did they join?
Sir, it may be class. Maybe class.
Am I audible to everyone? Yes. So small n equal to, this is small n equal to total number of turns per unit length or length. Length is called as small n, where this small n is capital N by L, where capital N is the total number of turns of a solenoid, and theta 1 and theta 2 are the angles subtended at P by end turns as illustrated in figure 7.9. See here. This is the figure. So don't confuse with this figure. I will tell how this figure is going to draw. This is a cross-sectional view of a solenoid only. Okay. And theta 1 and theta 2 are the angles subtended at P. P is the what? Field point. At field point, these are the angles made from the vertical solenoid ends, right? And also show that if L far greater than A, what is the L here? L is the total length of the solenoid. What is the L? Total length of the solenoid. What is the A? A is the what is the A? A is the radius of the solenoid. If L far greater than A, right? Calculate this magnetic field intensity at the center of the solenoid, which is H equal to N into I into AZ only. Okay, so these are the two things which we are going to solve for this given problem. Okay, now see this diagram here. If I cut this solenoid into two pieces, that means at this cross, if you take a cross-sectional view, if I cut this solenoid at this particular point, if you make this solenoid into two halves, now how it will look like here? If you take a cross-sectional view, how it will look like? If you take the particular conductor at this particular point, how the current is flowing? I mean, it is coming out or going into the paper. As the current is flowing in this fashion, can you guess what is the current flow in this particular point? If you cut this conductor at this particular point, is it coming out or going into the conductor?
Coming out.
Coming out. So if the current is coming out, how to denote that vertical coming out of the current from a conductor? A circle with tell me, a circle with dot. Study about these things in missions, in armature reactions. So circle with the dot, circle with the dot, circle with the dot, circle with the dot. Okay. And at lower end, how the current is flowing through the conductor? Please respond. At the lower end, how the current is flowing through the conductor? Current is flowing into the paper. Into the paper means what? It is away from the observer. Away from the observer. How to represent the current flowing from the observer, away from the observer? Circle, inside a circle, a cross. Inside a circle, a cross. Inside a circle, a cross symbol. Inside the circle, a cross symbol. So that means this diagram, what this diagram represents? A cross-sectional view of this dot. This dot is what? There is a conductor like this. A conductor, a current is coming towards the observer. Dot means current is coming towards the observer. And cross means current is flowing away from the observer. This is only a cross-sectional view of a solenoid here. And where the field point is exist here? Where the field point is exist? At the on the axis of the loop. How the axis of the loop is exist? This is the axis of the loop. Somewhere the point P is here. This is the point P, where the magnetic field intensity is to be calculated. Okay. And what is this length from here to here? What is this length? From axis of the loop to this point, this is the radius of the solenoid. The radius of solenoid is L, and the total length of this solenoid is L. Okay, length is L and radius is A, right? And here, from the axis, see how to calculate this magnetic field intensity at the field point P here. And he has given the angles here. Theta 1 and theta 2 are the angles subtended at point P by the end terms as illustrated here. See, now come to this diagram here. Now, is it clear? Everybody can able to understand this diagram? This is what a cross-sectional view of a solenoid. P is the field point. P is the what? Field point, and theta 1 is the angle. Theta 1 is the angle from where axis of the solenoid with this lower end. This is called a lower end. What is this? Lower end of solenoid, and that means starting end. Lower end means starting end of the solenoid. This is called upper end. Upper end of the solenoid. And theta 1 is the angle made by this axis and the line joining from the point P to this what? Lower end. That is theta 1. What about the theta 2? And if you want to calculate H, and imagine that it is placed along the z-axis. Imagine that it is placed along the z-axis. And instead of taking total length here, usually what is the procedure we are following here? Instead of taking a total length here, how much length you are taking here? What is the usual procedure you are following? Instead of taking a total length, you have to take which length? Differential length dl. But as it is placed along z-axis, imagine it is placed along the solenoid is placed, because if you want to solve any problem, you have to imagine particular coordinate system. The coordinate system is the Cartesian coordinate system only, and the solenoid is exist along the z-axis. If it is placed along the z-axis, what may be the dl here? Tell me, what may be the dl? dl will be what? dz. dl will be what? dz, because it is placed along the z-axis. So this is what a dz. This is what a dz, and theta 2 is the angle which is made by this axis with respect to this line. This is the line. Okay, this is what theta 2. This is the line. This is upper end. So this is very, very important to understand this concept. This is upper end. Theta 2 relates to upper end and theta 1 relates to lower end. Okay, now? Now, one more angle is that, so as we have taken this differential length dz, and if you draw a line from here to here, with respect to this field point, from this dz, it is making an angle called theta. Okay, this angle is known as a theta. So theta is the angle made by this field point with respect to dz. This is about a solenoid diagram. Okay. Now we are going to calculate. Magnetic field intensity at the field point P here. Okay. So any doubts in this? Anybody have any doubts in this? So this is what a solenoid length L, a radius A consisting of number of turns of a wire carrying current I. Right? We are going to calculate this derivation and this derivation, where n equal to total n by L. Okay. See, let us come to this derivation. Let me derive this derivation in canvas here. I'm adding +1 to get 2. So 1 plus 2 equals 3 here. So how do you get this 2 here? See here. Again, I'm explaining here because it is somewhat little bit confusion here. This is a magnetic material. This is a what? Magnetic material or core of a material. Example is a limb of a transformer. And here, this is the copper wire which is wound on this core. This core. So this is called a solenoid. Solenoid. And if the current is flowing through this solenoid, so current is flowing in this. Imagine in 3-dimensional here, if the current is flowing in this fashion, and the number of turns are capital N, and the total length of the solenoid is L, and the radius of this solenoid is A. Now we are going to calculate the magnetic field intensity H due to this solenoid. H due to this solenoid. So for this we have to, and we are going to calculate this magnetic field intensity at on the axis of the loop. So imagine there is a field point P here, field point P, and if you take the cross-sectional means if you cut this solenoid into 2 pieces at this particular point. You cut this solenoid at this particular point. And again at this particular point, the current is coming out. Coming out means it is denoted as a circle with the dot. Again I am drawing so that you can understand clearly. Okay. And how the current is flowing here into the conductor. So away from the observer, cross, circle, inside a circle there is a cross, inside a circle there is a cross symbol. Here, now this is the axis of the loop. This is what? Axis of the loop. This is the axis of the loop. At point P, we are going to calculate H. And it is placed along the z-axis. This is z-axis. It is placed along the z-axis. And this is the lower end of the solenoid. This is what? A lower end of the solenoid. And from the field point P to this lower end, let us take the angle is what? θ1. And this is lower end. Are you understanding here? This is upper end. This is upper end. Let us draw a line to the upper end. To the upper end. Again, it is making some angle called θ2. And the length of this solenoid is, let us take L. Length of the solenoid, let us take L. So here, instead of taking a total length, what is the procedure we are following? You have to take a differential length dl at this particular. So the total length is L. Total length is L. Here I am taking a differential length dl. Here like this, you have to take a differential length dl. So here the differential length dl. So dl equal to dz. dl equal to dz. At this differential length dl, so there are circular loops and there is a spacing between the circular loops. Okay. Now again another angle you have to draw with respect to the differential length dl and with respect to this axis, and there is a angle called theta. There is an angle called theta. And if you draw a perpendicular line from differential length to this axis is this. Axis is this. Now, can you guess what is this length? From the axis of loop to this differential length. What is the height of this one? Let us take this is a triangle. This is right angle triangle. What is this length? Please respond.
Yes.
Very good. Yeah, because it is a radius of the solenoid. It is what? Radius of the solenoid. And as it is placed along the z-axis, from P to this perpendicular distance, let us take it is a z. As it is placed along z-axis, from here to here, P to this is a z, and this is angle theta. I will come to this triangle later. Okay. Now, so everybody is following. Anybody have any doubts in this? I am going to derive the expression. Once you understand this thing clearly, this is theta 1. Clearly, the remaining things are very, very easy. You have to understand what do you mean by a solenoid, what is the cross-sectional view of the solenoid. Okay? And here, one more thing is that if I having a straight conductor like this, then if I take DL, current is flowing, then if it is placed along z-axis, and it is a DL. What is the DL? DL equal to DZ. What is that? DL equal to DZ. But here, is it a straight conductor? See, is it a straight conductor or loop type of structure? Please respond. Solenoid means it is a coil. It is an inductor. Inductor is placed or inductor is wound on a core, magnetic core. Is known as a solenoid. Is it a straight conductor or loop type structure? Please respond. It is a loop type structure. How many loops are there here? How many loops are there? So then if n number of loops are there, then loops are there. How to for a straight conductor DL equal to DZ. And in the similar manner, let me take another one here. If you take again, I am going to try again a solenoid here. See here, from here to here, see, from here to here, and back side also there is a conductor. From here to here, can I take this is a one circular loop? Please. Can I take this is a one circular loop? One circular loop. And the current is flowing in this fashion. Current is flowing in this fashion, and the radius is A, and the radius is A, and the field point is at the distance of Z. Field point is at a distance of Z. That means height. The height of this field point is Z. So then what will be the magnetic field intensity due to a single loop, single circular loop H? Can anybody tell me? We have already discussed. We have taken a circular loop type of conductor which carries a current I, and we have taken a field point at this particular point and at a distance of Z, and this radius is A. And the current is flowing like this. What is the magnetic field intensity at this particular point, field point P? Please, anybody tell me? Roll number 46. What is the magnetic field intensity due to circular loop? Dattatreya?
Yes, sir.
Yeah, tell me what is the magnetic field due to the circular loop at the field point P? You already derived. Tell me the formula. I into
I into R square AZ bar by
R square means here A square. A square divided by 2 into
A square plus Z square
very good. A square plus Z square whole to the power
power
of
3 by 2.
3 by 2 in the direction of what? Axis of the loop. What is the axis here? Z axis.
Z.
AZ. Okay. This is what due to a only one circular loop. But how many circular loops are there here? Please tell me. How many circular loops are there here? There are n number of circular loops. At this differential length dl, there are some vertical, some circular loops maybe exist. Some circular loops maybe exist. How to write that one here? N. What is that n? That n equal to total number of turns by that particular length. Okay. In that case, here, how to write the dl here? Or as it is a current element, how to write that current here? You have to write that current as I into dl. What is that? I into dl. Right? I into dl you have to write instead of I for a solenoid. How to write the current? I into dl here. But dl is equal to what? What is the dl here? dl equal to dz. What is that? dl equal to dz. But as there are some loops are exist under this length, that is nothing but a n. So we have to write n into dz. N into dz. So if you take this solenoid type of vertical structure or solenoid, then you have to take instead of the current I, what should I write here? I should write as I into dl into, instead of dl, what should we write? I into n into dz. Okay, so n into dz come extra if you consider n number of loops. Okay, so here as I have taken a differential length, what may be the magnetic field intensity? Is it total magnetic field intensity or differential magnetic field intensity? This is total length is L. I have taken only a differential length at this particular point. What may be the magnetic field intensity? It will be a H or it will be a DH? Please respond. As you have taken a single loop, there is a H.
DH, sir.
Yeah, very good. DH. Now tell me the formula for DH for this solenoid. DH equal to, instead of I, what should you write here? I into N represents number of loops under the differential length. Sir, pen ఇస్తారా సార్? See here. Yeah, tell me. So instead of dl, what should you write? N into dz. If a single loop is there, only dz, but n number of loops are there, n into dz here. Okay, n into dz into what? A square. A square divided by what? 2 into a square into z square. Into z square all to the power of 3 by 2. What is the unit vector here? Unit vector is AZ. Are you following this here? What is the differential magnetic field due to this solenoid here? DH equal to dH equal to I into N into dz into a square divided by 2 into a square plus z square whole to the power of 3 by 2. Because the solenoid is consisting of n number of loops. N number of loops, so that we have taken n into dz. Instead of current I, we are writing this n into dz as extra for this n number of loops here. Now, okay. So then, due to this differential length, again I am writing here dH equal to I into n into dz into a square divided by 2 into a square plus z square in the direction of az, right? In the direction of az. Now, see here in this problem, I am going to replace dz with these triangular formulas. This is a little triangle. This is a right angle triangle. This is what? A right angle triangle. Let me draw this right angle triangle separately here. And this angle is theta. And this length is z. And this height is a. In this, can you tell me what is the cot theta in this triangle? Please respond. What is the cot theta in this triangle? Hello. What is the cot theta?
Z by A, sir.
Z by, very good, Z by A. From this, what is the Z? Right angle triangle, again I am writing here. This is theta and this is Z and this is A. And this is cot theta equal to Z by A. Then Z equal to A into cot theta. And what will be the dz here? A into, what is the differentiation of cot theta with respect to d theta? Please respond on differentiation of trigonometric formulas. Minus cosecant square theta d theta. Minus cosecant square theta d. So dz equal to minus a cosecant square theta into d theta. So let us substitute dz and z values in the dh here. What is the dh here? Differential magnetic field intensity. I into n into dz into a square divided by what? 2 into, please, a square plus z square whole to the power of 3 by 2 in the direction of az. Okay. Now, let us substitute I into n. Instead of dz, let us substitute here minus a cosecant square theta d theta. Minus a cosecant square theta into d theta. A square divided by 2 into a square plus, what is the z square value? Instead of z, let us substitute a cot theta. Why you are doing all those things means to simplify the integration. That's it. A cot theta whole square whole to the power of 3 by 2. That means a square cot square theta. Right? So in here a into a square. That so there is a minus, right? A cube cosecant square theta d theta divided by 2 into, let us take a square as a common in this, and if you take a square as a common, A square whole to the power of 3 by 2. Inside the bracket, what remains here? 1 plus cot square theta whole to the power of 3 by 2. So what is the value of 1 plus cot square theta? How to write 1 plus cot square theta? 47. Venu, respond now.
Cosecant square theta.
Cosecant square theta. So write this as cosecant square theta. So cosecant square theta whole to the power of 3 by 2. So 2 will get cancelled out. Then what remains here? So this total term will becomes what? Cosecant cube theta. Okay. Now see here. Here also square and this square will get cancelled out. The denominator, what remains here? This is a cube and a cube. A cube will get cancelled out. And here there is a cosecant square theta. Here cosecant cube theta is there. Okay, then 1 by cosecant theta. Right? And I, n, and you can take 2 as a common like here. So if you simplify this what you call numerator and denominator, finally what we will get here? dh equal to what? I into n into d theta divided by 2 into cosecant theta. Okay? 2 into cosecant theta. And minus is there. Minus is there. Chapam.
Minus on the end.
Okay, right. Now, this is a differential magnetic field intensity. Then, what is the total magnetic field intensity at the field point P? We have to do integration. H equal to integral. Can I take I and n out of the integral? Minus I into n out of by 2. I n by 2. 1 by cosecant theta d theta. And what are the angles for d theta here? One is upper angle, another one is lower angle. What is the lower angle here? With respect to lower end, theta 1. What is the angle made by the axis of the loop with respect to upper end? Theta 2. So theta 1 and theta 2 are the angles. See here. Minus I n by 2. What is the 1 by cos theta? Theta 1 to theta 2. 1 by cos theta is?
Sin theta.
Sin theta d theta. Now, let us integrate this. So h equal to minus in by 2. So integration of sin theta is minus cos theta. Minus cos theta integral theta 1 to theta 2. Okay, so already there is a minus. So minus both will get cancelled out. So in by 2, let us substitute these angles here. Cos theta 2 minus cos, right? So finally, what is the h? H equal to I into n divided by 2 cos theta 2 minus cos theta 1. Yeah, we have forgotten one thing here. It is along which axis, which unit vector? Az is there. Az is there. Az is there. In the direction of Az. So this is what magnetic field intensity due to a solenoid at the field point. So remember this H equal to I into n. I into n by 2 cos theta 2 minus cos theta 1 in the direction of AZ. Okay, let us verify whether you got the same derivation or not in this. So let me open that textbook PDF and stop sharing this whiteboard. I'm opening this. See here. All of you see this one. H equal to what? H equal to I into n. What you have got? I into n or n into I by 2 cos theta 2 minus cos theta 1 in the direction of what? AZ. Did you get the same answer or not? See here. So this is the derivation in the textbook here. Each and everything will be there. Everybody go through that. So dh equal to IDL A square divided by 2 into A square plus Z square. After completion of this class, everybody go through this textbook. So instead of writing DL, what you have written? N into dz. Now you can understand what is n into, why you have written n into dz. Okay. Next, right? And initially we discussed what is the n here? N equal to n by L, total number of turns by L. Okay. Then finally, this is the answer which you have got. H equal to ni by 2 cos theta 2 minus cos theta 1 in the direction of AZ, where n equal to n by L. Okay, small n equal to capital N by L, total number of turns per length. Okay. Now, next one, what he wants to calculate here, again he wants to calculate also show that, also this is finished sum, show that if L far greater than A, at the center of the solenoid, H equal to N into I into AZ. What is that? And the condition is that L is far greater than A. L is far greater than A. Okay. So let me derive that one also. Anybody have any doubts so far? So in this derivation, if you have any doubts, you can ask them. Venu?
Yes, sir.
Shall I continue?
Yes, sir.
So let me derive the remaining thing also. For that, at the center of the loop, exactly at the center of loop. So now come to the initial diagram here. So imagine it is at the center of the loop. At the center of the loop. So let me draw another diagram here. So this is the z-axis. This is the z-axis here. And the field point is at the center of the loop. The field point is at the center of the loop. Okay. Now, let me redraw this diagram because it is a little bit confusion here. There are 5 more minutes are there. So let me finish this. So all these are crosses and this is z-axis. And imagine at this point P, be the field point. Where it is located here? At the center of the loop. At the center of this. This is what? A lower end, and this is upper end. This is lower end, this is lower end. This is lower end of the solenoid. This is upper end of the solenoid. Now, so with respect to this lower end, what is this angle here? With respect to z-axis, we imagined that this is the angle of theta 1. Okay? And what is this angle here? What is this angle? Theta 2. What is this angle? Theta 2. And if this total length is L, the total length is what? L. Can you guess from here to here what may be the length, as the T is exists at the center of this solenoid? Yeah, can you guess what is this length? The total length is L. If it is at the center, what may be this length?
L by 2.
And this is also L by 2. This is L by 2 and this is L by 2. And this is the angle is theta. And what is the height here from here to here? What is the height? Chappadam. What is this height? Radius of the solenoid is A. Radius of the solenoid. So this is one right angle triangle. Okay. And this length is L by 2. This length is A. From Pythagoras theorem, what may be this length? Please respond fastly. We have only left with 5 minutes. What may be this length? This length will be L by 2 whole square plus A square under root. Okay? Right? Here also, this height is A. This height is A. And this length is L by 2. And it is also a right angle triangle. But if it is a theta 1, can you guess what is this angle? From z-axis with respect to this one, this is theta 1. How to write this angle? So the total angle is 180 degrees. Total angle is 180 degrees. And this angle is theta 1. How to write this one? 180 minus theta 1. Okay? This is the angle. This angle is theta 1. This angle is 180 minus theta 1. And what is this length? This length is from the Pythagoras theorem, L by 2 whole square plus A square under root. Okay. Now, tell me, what is the cos theta 2 here? From this right angle triangle, tell me what is the cos theta 2? Please respond. Cos theta 2 equal to? Menu?
L by 2 by hypotenuse.
L square by 4 plus A square. Very good. What about this? Here you have to, if you take this right angle triangle, you have to take cos of 180 minus theta 1. So cos of 180 minus theta 1. Yeah, tell me what is the cos of 180 minus theta 1 from this diagram? Again, L by 2 divided by L by 2 whole square plus A square under root. Okay, so cos of 180 minus theta 1 equal to what? Minus cos theta 1. Minus cos theta 1 equal to this. L by 2 under root L by 2 whole square plus A square. Now we have cos theta 1 and cos theta 2 values. Why it is L by 2? Because the field point is at center of the loop. So we are going to calculate H at this particular point. Okay. Now let us substitute these cos theta 1 and cos theta 2 values in our derivation, what you have derived earlier. Please, let me finish this. What is the H here? H at any point on the axis of the loop. If the field point is anywhere, then what is the H? N into I divided by 2 cos theta 2 minus cos theta 1 in the direction of AZ. So let us substitute these values. So Ni by 2, what is the cos theta 2 Venu? L by 2, L square by 4 plus A square minus, what is the cos theta 1 value? we have calculated minus cos theta 1. So then what is the cos theta 1? Minus of
L by 2
L by
by
L square by 4 A square. It is in the direction of AZ. Kada? Now, so minus and minus will get a plus here. Now, if you add these things, both terms are same, then this becomes what? N by Ni by 2, right? So 2 into kada? 2 into L by 2, L square by 4 plus A square. Root in the direction of AZ. Now, in the problem itself, he has given what is that condition? L is, please tell me, L is far greater than Chapanama. A, the length of the solenoid, very long solenoid, and the radius of that solenoid is very small when compared to that length, like this. The radius is very small and the length is very large. Let us take this 0.1 and it is 100 meters like that. If we compare 100 meters with respect to 0.1, we can neglect this, right? A. Yeah, if you neglect this A, that means if you compare L with A, we can neglect A in this equation. If you neglect A, please tell me, if you neglect A and this becomes 0 when compared to this, then only L square by 4. That means it becomes L by 2. In denominator, it is L by 2, right? So in numerator, L by 2, sir, it is L by 2, okay? Are you following or not? This is here also there is 2 and in denominator there is a 2. What remains here? What remains here in this equation?
Ni in the direction of AZ.
This is very important. Very important. Magnetic field intensity at the center of the solenoid is Ni into Az. Ni into Az. This is the derivation. Okay. So this will be helpful to design a transformer. If you want to design a transformer, you need a flux, right? You need a flux. How to get the value of the flux here, right? How to get the value of flux? What is the flux density? Flux by area. And how to get this flux equal to B into A. Okay, flux equal to what? B into A. And I know area, and how to get the B? B should be calculated from H only. What is the vertical relation between B and H? B equal to mu into H. So you can calculate H from this formula. Okay. Once we get H, we can calculate magnetic flux density. Once we calculate magnetic flux density, you can calculate the flux. And if you calculate the flux, you can calculate the EMF equation, EMF of a transformer. What is the EMF equation of transformer? E equal to 4.44 into number of turns into flux into phi m. Okay, na? Into frequency. So if I want to design a particular transformer for a particular EMF, compulsory you should know this formula. That means if you want to design a particular transformer, anything, so these EMF basics are very much required. Okay, for designing purpose, we are going to use this formula, right? So the magnetic field intensity at the center of the loop equal to N into I into Az. This is one formula. At any point on the loop, the field point is exist on any point. What is that formula? H equal to Ni by 2 cos theta 2 minus cos theta 1 in the direction of Az. Okay. So this is about magnetic field intensity due to which one? Solenoid. Very important. Right. So I stop here.